Right. So similar to Brian Anderson's talk, I'm going to spend quite a long time in introducing things which are not generally familiar to the audience, so less familiar subjects. And so we're going to deal with two domains of knowledge. So one is famous in mathematics, the so-called root systems. Another is delta interacting particles in one dimension. And so we are going to, more to the point, we're going to concentrate on two-dimensional root systems and three delta interacting particles in one dimension. So we're going to bring these two domains together and see what the interface between them is. And then, of course, I mean, you can see it's a Newton cradle, but now a Newton cradle with balls of different masses. So that's the important ingredient. So in particular, if you have a Newton cradle with one infinite mass, one mass 3 and one mass 1, this realizes the root system which is called G2. Or if you take two equal masses with this strange mass ratio and so forth, and mass 1, this is another root system, which is called I to 10. But the funny thing is that if you plug the actual masses in, so the mass ratio will be pretty close to a set potassium 40 lithium 6, and so we'll see in the end that there are a few mass combinations that by accident realize what we want. And what we want is really a root system. And
Maxim, I can't do the roots in my head. How close are these?
Who?
The square root of how close is this?
How is it's within 1%. But I'll show another example with less within 1%. So I will show one example where it is within 1/10%. So it's 0.8%, and that's my favorite example. Not this one, the other one. So no, those are the numbers are no. It's numerology. No, I'm not claiming nature. What?
Like your talk has exact advertisement, so for you 1% is infinitely far away.
Oh, right. Well, there's also always a width. I mean, for any effect you have a width, and the question is, well, right? But that's
if you are a lousy experimentalist, it's not infinitely far away.
Right.
Depends on the quality of your experiment.
And so the historical origin for this project is one phrase I read in a famous book on beta ansatz by Michel Godin, who analyzes the relationships between integrable many-body systems and kaleidoscopes. So, and kaleidoscopes are systems of mirrors that realize only a finite number of reflections and so on and so forth. And so kaleidoscopes are very important in mathematics because some of them, namely the crystallographic kaleidoscopes, they allow you to classify the Lie groups and so on and so forth. So what he said was that there are classic root systems which are interesting, which are important to us physicists, and exceptional or exotic. They're not physical at all. And I, being pretty attentive to details, let's call it that way. This phrase really bothered me for a long time, but for almost 20 years. And so, to briefly give you the history, to briefly explain why I'm introducing something that appeared in the early 60s and was mainly developed in the early 60s. So let me show you how the effects I'm going to present could have been overlooked and why they were overlooked. So the story of the relationship between the root systems and integral models really starts from Girardot's model. So those are n hardcore bosons in one dimension, and they give you an n hard boson realization of what would be called an an minus 1 root system. So then in 63, Liebling generalized this model to finite strength interactions. Later, McGuire and Godin analyzed so finite strength interactions in many details, and they gave what might constitute the proof that this A system is the only one that is relevant to finite strength interacting bosons. And so my theory that the field of mathematical physics was so excited with finite strength delta interactions that they forgot about the hard cores. They forgot to actually explore the whole area of the hard cores. And so in 2013, I'm returning to hardcore, not bosons, hardcore particles. So those are different masses. They have different masses in general, and thus neither bosons nor fermions. So let me briefly tell you what root systems are. They're immensely important in mathematics. And actually they're used for almost everything. So what is a root system? So it's a collection of vectors that first thing it does is so if it's a root system in a d-dimensional space, it's a collection of vectors that spans the space. This is easy. Then for a given direction, there is a given vector, and it's negative. If those are only two vectors that are allowed along a given direction. So namely, along a given direction they have only one length. So a more important property is that this set is, if I start building mirrors whose normals are my root vectors, then this system of vectors is closed about these mirrors. So in this you can see where kaleidoscopes come in, and the last property, which is less trivial, is that if I compute a difference between a given root vector and its mirror image with respect to one of mirrors, this difference is going to be integer multiple of the actual normal that was used to generate this mirror. And this property turns out to be important for being extended to periodic boundary conditions. So that this last property allows you to actually build periodic sequences of mirrors. So now, as I said, they're immensely important in the world of mathematics. It's a whole universe. It allows you to classify the simple Lie groups, which is a big part of the modern mathematics. And this is not what we're considering today. So we're considering today a much simpler application of the root systems. So they are used here to generate exactly solvable Helmholtz type problems. And Helmholtz problems, it's just a free particle, so a free quantum particle, so kinetic energy plus this is your energy, with non-trivial boundary conditions, so with some boundary condition on a polygon, and the boundary condition relates the normal derivative, normal gradient of the wave function to the wave function itself. And then the coupling constant that's a technical detail, it can take at most two possible values, depending on whether the given root is. So only two possible values. We'll discuss that. So, and the way root systems come in is that so these polygons, they're nothing else but they're built out of mirrors, which are normal to the roots, and so. If a very important property also of the mirrors built by the root systems is that these polygons, they tile the space if you flip these polygons about their own sides, which is a highly non-trivial property. So they cover the space if they flip about their own faces generally. And so, and I won't explain the whole, I mean, the mechanics in all details, but the integrability of these polygons, it has three ingredients. So first, it indeed this flipping tiling property. Second, you use the method of images to solve this problem. So you flip and repeat your solution with a given plane wave. And the third thing is a Young-Baxter phenomenon that basically says that the result of this operation won't depend on the order in which you've hit respective mirrors. And so remember, there is a coupling constant that is going to become our strength of the delta function. And so for a different coupling constant, you get different solutions, and I couldn't resist. I'm showing just because I like it. So that's that. These are hardcore bosons. These are going to become hardcore particles. So you see there's an exact node at the mirror, and these are finite strength interactions, but not actually particles. So it's just a triangle billiard so far, and it's not going to become three particles. So now, as with any nice set of axioms, you may start thinking about what happens if you remove one of them. And the most natural axiom to remove is to remove this axiom of periodicity, this axiom that leads to periodic sequences of mirrors. And what you are left with is in fact two mirrors that are not extended to anything periodic, but still, so you can help a problem in between these mirrors. And in particular, this one is an important. This one is the symmetry between two mirrors with an angle between them pi over 5, and this symmetry is if you look at the famous mosques in Spain. So what you see on the ceiling is exactly this symmetry, and also it's a symmetry of most popular symmetry of quasi-crystals. And here it's the same thing, but even nicer. So while alcove is a polygon that tiles the space by flipping, while chamber is a wedge that tiles the space by flipping. So it has one open side. And so that's precisely what it does. So not related to today's discussion, you can also think about removing the second axiom, but not the fourth. So the fact that all routes along a given direction have the same length, and this is tightly related to the classification of the Cologero-Sutherland models. So particles with interactions 1 over r squared, and this is not for today. And finally, just to tell you how many of these root systems we have. So there are 4 which are called classic. So A is basically a symmetry of tetrahedron related to n delta redirecting bosons. B, C, and D is a symmetry of Q cube, and this is related to delta interacting bosons, which was also strange interactions where not only particles with the same coordinate interact, but particles with two opposite coordinates interact. And this is also not quite physical. So there are exceptional root systems. So G2 is related to to nothing. It just exists in 2 dimensions. To a nice triangle with the angles 90, 30, 60. F4 is a symmetry of the only exceptional platonic solid in 4 dimensions, which is called 120 cell. And these 3 are real monsters, and that they correspond to nothing. They don't even correspond to the platonic solid. So H's are, so I's are just symmetries of a wedge with angles pi over n between them. And BC, we're not discussing it here. So and so what we discussed today is G2 and this I system. So all 2 dimensional. So what about particles? So while Helmholtz problems we discussed, they live inside polygons, so they are problems with boundary conditions. So they're sitting inside some closed surface, and there are boundary conditions on the surface. What we have with particles is different. So what we have with particles is, in fact, so first of all, so we start from 3 particles, generally with n particles, with some masses. You can always transform your coordinates, so you can always eliminate the center of mass motion of these 3 particles. So what you will get for the relative motion is a particle of a given mass, abstract, in 2 dimensions, that interacts with 3 regions of delta functions. So it really lives in a 3-dimensional space, or in a 2-dimensional space, and so there are 3 lines of a delta function, and these delta functions, instead of introducing boundary conditions, they introduce what is colloquially called the jump condition. So it's because you approach your wave function, say, approaches this surface. It has some value of a gradient of the wave function on this side. The gradient of the wave function is allowed to jump on the other side, and this jump is related to the strength of the delta function on this line. And so the art of, well, actually the essence of the beta ansatz, the essence of all the integrable problems with delta interacting particles is in fact to map this situation to the Helmholtz polygons, to the polygons solvable by via root systems. And there are 2 ways how one can map to another. So one way is this. Oh yeah, okay. So right, and this is what happens with periodic boundary conditions. Sorry, okay. So with periodic boundary conditions, you get periodic lines of delta functions, and now instead of each domain, each sector correspond to a particular order of particles. All we can only say is so each sector would correspond to a particular parity of the ordering of the particles. So for delta functions, for periodic boundary conditions, what you get is 3 periodic size sequences. So now, so 2 things must happen, as I said. So one is these lines of the delta interactions should form a corresponding either wild chamber or wild alcove. So one of these polygons generated by the root systems. So the second thing that should happen is that these jump conditions must map to the conditions to the boundary conditions on this Helmholtz polygons. And this could happen in 2 different ways. So one way is well known, again, since 60s. So you concentrate on particles of equal mass. So you assume that they're bosons. So thus the wave function is going to be symmetric with respect to the flips. And if your wave function is symmetric with respect to the flip about the particular delta ridge, you can relate the gradient. You can relate the gradient of the wave function on this side to the gradient of the wave function on that side. And since they are related, it generates effectively a boundary condition for the gradient of the wave function on the inner gradient of the wave function just inside the particular polygon. So this is, we relate these 2, and thus it constitutes a boundary condition for the gradient on the inner side. And this is precisely what happened with the Lieb-Lininger condition on the 60s, in the 60s. But there is another way. So and the other way is this. So you can simply so you can only concentrate on hard cores, and for the hard core boundary conditions, one inner side of the polygon doesn't talk to the outside outside of the polygon, and thus, well, psi equals 0 is a psi equals 0. So it can be considered as both as a boundary condition and as a jump condition. So this the system inside the polygon doesn't know about the outside, which also means in particular that some combinations of masses they can be integrable for one order of particles, but not integrable for another. And that's precisely what happens. That's precisely what no, not in this case, but there was some other. Yeah. So in this last case, this is precisely what happens. So and that way we can identify two cases. So one is relatively trivial. So two particles of the same mass at a hard wall, so they can still interact via a finite strength delta function, but plus a hard wall. And the less trivial case is particles of masses 3, 1, and infinity, and a hard wall, and this thing can be even put on periodic boundary conditions and also solve with that. There's another case. So here we have to release the condition that this polygon is closed. So it's just thus here we have to work for integrability. We have to work in the open space with no periodic. We should have to release periodic boundary conditions, and there for each magic angle between two mirrors, for each integrable case, which is parameterized by this integer n, there is a continuous family of mass ratios, which of course, so that's where numerology starts, right? So you have a sequence of integers, and for each sequence of integers you have a one parametric continuous family, and well, we have many atoms, even more pairs of atoms, right? And so you could find something interesting there. And
can all these cases be generalized beyond three particles as the first case?
No. That's precisely the thing. I mean, this is. I think. I mean, mathematicians would say I explored all the root systems. No. There's no generalization. So we'll talk about many-body later, right? But as an exact effect, I do believe this exhausts everything. And so right. So for hard cores.
The first one can. The first one you can.
First one, actually, first three can.
Yeah.
No. First one can. Yeah, first one can, and the rest of them no. So now for well, actually this one right. So. Right. And now let's concentrate on the last case. So again, three particles in one dimension with magic mass ratios. And how more esoteric can it be? So, but first of all, let's see if we can get these mass ratios. So I consider two different cases. So in one case there are two heavy and one light particle. So and there are two combinations. So one is lithium-7 cesium, and another is lithium-6 and potassium. So and they realize I26 and I210. So another case is one supermassive or a wall, and one light, one heavy. So there is root system 8, and this is sodium and cesium. And now the following idea. So of course, nobody, no experimentalist in his or her right mind would make an experiment with three particles, especially that it's not. No, wait. What? What with three? What did I say?
Philip does 1, 2, 3, 4, 5, 6.
Oh yes. So sorry. Yeah. Okay. Right. Not.
It's clearly not in his right.
But now let's look at what the actual physical effect is. it's better to illustrate on something which is even simpler than what we discussed. So that's the example of what's called a corner reflector. And all of us know particular manifestations of corner reflectors. So typically it's three mirrors at 90 degrees between them, and the property is that when you shine light on them from any direction, so the light entirely returns to the same direction. And then on my walk to here, I found one experimental demonstration for that. As you can see, I mean, this is a reflector from some bike reflectors I found on the street. and I can turn it around, but the light completely returns to the origin, to the laser.
So it's under some localization.
No, not quite. But this is not the effect we're interested in. We're interested in something much simpler than that. So what I want to concentrate on is that I have three mirrors here, but the outcome, the outgoing beam, its direction does not depend on the order in which my light beam hit these mirrors. So in principle, and so let's see these three mirrors for the radar. In principle, the result should depend on whether my sound wave hit here and then here and then here, or here, here, or here. But for the magic angles between the mirrors, so for a given direction of the incoming beam, the outgoing beam goes in a single direction, and this is the property which we're interested in. So that's precisely what I wanted to illustrate. So so these two mirrors 90 degrees, they would correspond to something, very simple. So let's consider two situations, one generic, one not. So it's super simple things. So one massive particle, but not in infinited mass. Two particles of the same mass and smaller, and for simplicity, these two particles don't even interact with each other. So generally speaking, the outcome will depend on whether a faster particle have hit the massive particle first, or the slower particle have hit the massive particle first. So the outgoing momentum distribution for the same initial momentum distribution, which is these two peaks, will have two different momentum distributions. So depending on the order in which these two collisions happen, depending on whether the fast hit first or the slow hit first. But if we nail our massive particle with the nail, and or give it an infinite mass, so we'll get one of the magic angles between the mirrors, and what will happen is that the outgoing momentum distribution won't depend anymore on the order of these two collisions. They will just flip their velocities, and so we'll get the same result regardless of the order. So one would expect that in a more complicated situation, in a particular three-body collision, the entropy increase in the integrable case per three-body collision is less than the entropy increase per three-body collision in the generic case. And so what we did, so first of all, we took indeed the truly honest to goodness integrable case of masses 3,1 and infinity with periodic boundary conditions, and compared it with a generic case which is right in between two integrable cases. So these are the mass ratios, and no surprise. So in the integrable case, increase of the entropy, and entropy in this case is just the how uniform the orientation of this relative motion velocity is. So some measure of ergodicity. So entropy stops somewhere short of the absolute of the ergodic limit. So in this case, it keeps growing. So there is no much surprise here. But now, so now what we do is this. So we take something which has a few integrable angles in it, put it in periodic boundary conditions, thus spoiling integrability, but still keeping. So in some three-body collisions, we still have integrable angles, and compared with something generic. And so what we see is that in this case, that contains that is not exactly integrable, but some three-body collisions happen at integrable angles. Entropy increase is much slower. And so the expectation is that if we simply, as Jason said, I mean, if we simply take this mass combination and look at the many body system, we'll still have a slowdown of thermalization at integrable angles, and this is exactly the plan. So, but already already at this level, you can see that the actual integrability doesn't matter. What matters is integrability at the level of individual three-body collisions, and this I'll skip. So many thanks to collaborators. So this part of this work is done by the graduate student Frank Kao, who's here in the audience, and Stephen Jackson is our colleague from mathematics, and it was supported by NSF, ONR, and IFRAF, like Alan.